Talk about Louis de Broglie. I don't know. Let's say de Broglie. Basically, what he postulates, right, is that if light is acting as both a particle and a wave, maybe it's true that small things like small objects, small particles like electrons or protons or whatever, can possibly also act as a particle and a wave. Heretofore, they've been thought of as just particles, but if we allow ourselves the possibility that it could be a wave, then this is how he projected that we would calculate the wavelength of this. Okay. Now, it turns out, by the way, that notably electrons do act like waves. This is why we can make images with them and magnify and whatever with electron microscopes. There's other notable examples. For example, electrons around atoms are in standing waves, and this turns out to be true. Okay, but just calculating this stuff is fairly mundane, right? This is momentum, so that's just mv. This is Planck's constant. That's the wavelength, the de Broglie wavelength, the de Broglie wavelength. Okay. The experiment that confirmed this, the first experiment, there's been many that have confirmed the notion that electrons can be particles and waves, are they take an accelerated electron beam. All of these have exactly the same velocity. This is, by the way, called a particle laser. They all have exactly the same velocity, and if they have the same velocity, they therefore have the same momentum and therefore the same wavelength, right? And so they've shown this on a nickel crystal. Well, a nickel crystal's got these little bands of crystal, right? It makes these little patterns. So it's a bit like a diffraction grating. And the electrons cause an interference pattern. And you get a bright spot, dim spot, bright spot, dim spot, bright spot, right? So more electrons would hit here, more electrons would hit there. And you could figure out it's just like a interference pattern. This nickel crystals patterns act like multiple sources of this. And they detected this, right? And that's a little bit spooky. Okay, we'll talk about that. But this pattern, exactly how does it? I mean, when I took quantum mechanics in college, I could calculate what this pattern would be, and it's exact. Only we calculate the probability that it's going to be here, the probability that it'll hit there, the probability that it'll hit there, and it works exactly like it's acting like a wave. But this works on electrons that are sent with the same velocity. You could send them one every minute. They're not even remotely near each other. So how do they create this probability distribution? They just do. Okay, let's do some calculations of this. Okay, so the first question is, what is the de Broglie wavelength of a baseball? This is a baseball, a fast pitch baseball, right? Okay, and the answer is that it's ridiculously small, and so baseballs don't really have any wave properties. Okay, but let's solve this. Okay, so momentum is mv, right? So p is h over lambda. Okay, so the momentum is 0.145. The velocity is 40. Sorry, I'm just laughing. 6.626 times 10 to the minus 34th divided by the wavelength, right? All right, so what I'm going to do is I'm going to go this divided by this, right? So 6.626 e minus 34. Whoops, what did I just do? I just typed 6626. 6.626. All right, times, divided by, parentheses, 0.145 times 40. And I get that the de Broglie wavelength, the de Broglie wavelength, is 1.142 times 10 to the minus 34th meters. So remember, this is joule seconds, right? This is kilogram meters per second. So a joule second divided by a kilogram meter per second is somehow meters. How is that? Let's see, a joule is a kilogram meters squared per second squared, right, times a second divided by, so times seconds over kilogram meters. I think it does. Seconds gets rid of the seconds. That gets rid of one of those. Yep, it's meters. All right. So the point here is not, watch the teacher do unit cancellation. The point here is that nothing is this size. The smallest thing that you could potentially make an interference pattern out of is a nucleus. Nuclei are 1 times 10 to the minus 15th meters. Okay, so you only notice wave behavior when you like interfere. You've got double slits that are on the order of the wavelength apart. Okay, nothing is this small. There's nothing that small. You can't make something that small. You'll never see baseballs interfere with other baseballs. Their wavelength is way too small. So wave behavior does not describe the behavior of baseballs. Not very much. But electrons, a little more. So let's look at the next one here. What is the velocity of a proton with a de Broglie wavelength of 600 nanometers? All right. So let's see. We've got to calculate the velocity. I think what we'll do is we'll calculate the momentum. So momentum is Planck's constant over the wavelength, right? So it's 6.626 10 to the minus 34 divided by 600 nanometers. All right, we can do this. 6.626 e minus 34 divided by 600 e minus 9. And that is the wavelength, sorry, the momentum is 1.104 times 10 to the minus 27th, and that's kilogram meters per second, because it's momentum, right? It's m times v. All right, and then that equals mv, right? So that equals 1.673 times 10 to the minus 27th times v. So I'm going to take this number and divide by this. So divided by 1.673 e to the minus 27. And it's moving along, the proton is moving along at a stately 0.660 meters per second. Ta-da. Okay, well, that's a slow proton. All right, let's look at the next one here. Through what potential must you accelerate an electron? Oh, this is getting trickier. So that it has a wavelength of 1.0 nanometer, right? And this would be shorter than a wavelength of light. Remember, light is, what, about 400 to 700 nanometers. So this would be like blue light. That would be like red light. Okay, so this is going to be way shorter. Okay, so let's see. I think, let's figure out the momentum of this electron. So the momentum is Planck's constant over the wavelength, so 6.626 over the wavelength, so 1 times 10 to the minus 9th. I think I can do this in my head, but maybe I can't. E minus 34 divided by 1 E minus 9. Is that going to be, what do I think it's going to be? 43rd or something like that. Oh, 25th. There we go. 6. I went the wrong way. See, it's a good thing I checked, right? So that is 6.626 times 10 to the minus 25th kilogram meters per second, right? Now, let's find the velocity of this. Right, so that's mv, that's our momentum, right? We start off with momentum. So that's 9.11 times 10 to the minus 31st. This is the mass of an electron in kilograms, right? Times v. So let's figure out v. Divide that by 9.11. And now the electron is going equals 727,332. They have to be careful with electrons. You know, little guys can get going faster than the speed of light. The speed of light, though, is 300 million. Meters per second. So this is safely below that limit, right? And there's no comma there. I don't know what I did there. Okay, so now we've got the velocity, and then what we can do is we can say, we can figure out the accelerating potential, right? So 1/2 mv squared, the kinetic energy, is equal to the change in voltage, right, times the charge, right? And we can just fill in what we know here. So 1/2 9.11 minus 31 times 727,332.6 squared is the change in potential times the charge of an electron. coulombs. There we go. There we go. So this will be joules. This will end up being joules per coulomb. Okay, let's try. Okay, so 0.5 times 9.11 E minus 31 times the number I just got squared divided by the charge on an electron. There we go. The change in electrical potential is 1.504 volts or joules per coulomb. Yeah. There it is. So all we did basically was we solved for the velocity and then used energy, right, to figure out how much voltage you had to accelerate it through to give it that much velocity. Okay. And this is just conservation of energy, that the electric potential turns into kinetic.